Again, welcome to statistics. This is DSRT 734 class. Again, this is our last lecture for the course. And our last topic is a non-parametric test for the runs test. So our main objective in this course, in this lecture, is how to use the runs test to determine whether a data set is random. Again, how to use the runs test to determine whether a data is random. So a run is a sequence of data having the same characteristics. And randomness is a very important concept in probability and also statistics. So in this session, we are going to discuss a method for determining whether a sequence of observations exhibit randomness. And to illustrate this concept, we will use the familiar coin tossing experiment as an example. And one characteristic of a coin tossing experiment is that in the long run, there will be approximately equal number of heads and tails. So again, a run test is a sequence of data having the same characteristics. And as we said earlier, the whole concept of run test is to determine whether a data set is random. So that's again our main objective. So each run is preceded by and followed by data with a different characteristics or by no data at all. Again, we're going to see an example soon. So the number of data in a run is called the length of the run. So for example, if I have a coin tossing and I toss the coin 10 times, I have 6 heads, 4 tails. The length of the run is 10 because we have 10 outcome and we did a 10 coin tossing. So the number of data in a run is called the length of the run. And also each run is preceded by and followed by another data with a different characteristics. So let's see an example here, finding the number of runs. So here we said a liquid dispensing machine has been designed to fill 1 liter bottles. A quality control inspector decided whether each bottle is filled to an acceptable level and passes an inspection P or fails inspection F. So determine the number of runs for the sequence and find the length of each run. So again, this is what happens, the observation. So we can see that we have PP, then we have 4F, then P, then 3F, then the rest are P. So this is the run. Now the number of runs or the length will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 16, the length. Now the question here said we should determine the number of runs for the sequence and find the length of each run. So the number of runs, for example, we have PP, so it's 1, and in the sequence is PP. Then next we have 4Fs, the sequence is 4Fs. So this will be the solution. PP, we have 1 run, the sequence again is PP. The second run, the sequence is FFF4. The third run is P. Fourth run, 3F. And the last run is again 6 Ps. So we have 1, 2, 3, 4, 5 runs. The length of the run will be 16 when we had all the P's and F's together. So here we said there are 5 runs. And the length of each run is 2, 4, 1, 3, 6. When we add all together, we get again 16. So runs test for randomness. So in this lecture, our main goal again is using the runs test to determine if a sample or data collected was collected randomly. So here we say run test for randomness is a non-parametric test that can be used to determine again whether a sequence of sample data is random. So here we want to determine if the sample we collected or the data that we collected from the population was collected randomly. In this case, again, we can use the runs test for it. And again, it's a non-parametric test. So here the null and also the alternative hypothesis for this test are as follows. We say the sequence of data is random. Then HA, which is the alternative hypothesis, we say the sequence of data is not random. Now we have two types of test statistics here based on the size of the sample. So we said that when N1 is less than or equal to 20, and also N2 is less than or equal to 20, the test statistics for the run test is G. G is the number of runs. As we saw our previous example, the number of runs was 5. But if the sample is greater than 20, so N1 is greater than 20, here we have two samples from population. So if both of them are greater than 20, then the test statistics will be the Z. So here we're going to use the standard normal table, Z equal to G. Again, G is the number of runs divided by the population mu, and then the standard deviation for the G's. And we have a special formula here to find the mu G is 2 times N1 and N2 divided by N1 plus N2 plus 1. And the standard deviation G will be square root of 2 times N1 and N2, parenthesis 2 times N1 and N2, minus N1 minus N2 divided by N1 plus N2 all square, multiplied by N1 plus N2 minus 1. So again, this is the formula for the test statistics. If our sample size are less than or equal to 20, then our test statistics will be the value of G. But if it's greater than 20, then we use the standard normal table. We find the Z. Again, Z is the G minus mu G over standard deviation G. Mu G is given, and then standard deviation G also is given. All we need to know is the size of the two samples. So we can see the formula here consists of only the size of the two samples. So let's go through the steps here. Performing a run test for randomness. As we said earlier again, run test is to determine whether a sample we collected was collected randomly or involve randomness. So here the first, again, this is also a testing, hypothesis testing. So we start with the same steps. First, we have to state our claim, which is to identify the null hypothesis and also the alternative hypothesis. So we need to state the HO and also we need to state the HA. The next step, we have to specify the level of significance. Most of the time, it's always given to us. When we are, based on the table that we are using, always the alpha will be 0.05. Here we are going to use the table for finding the critical value for runs test. So here we specify the level of significance. Use alpha equal to 0.05 for the run test. So we need to identify the alpha. After that, we determine the number of data that have each characteristics and the number of runs. So we need to determine the N1, N2, then the G. Then we determine the critical values. So if N1 is less than or equal to 20 and also N2 is less than or equal to 20, then we use the table 12. Table 12, again, is the critical value for the number of runs table. And N1 greater than 20, N2 greater than 20, we use the standard normal table because we're going to find the Z. So after we know the critical value, now we know the boundary between rejecting HO and also accepting HO or fail to reject HO. So what we need to find is the test statistics. Now the test statistics, we saw two ways. If N1 and N2 are less than or equal to 20, then we use the G. G is the number of runs. But if N1 is greater than 20 and N2 is greater than 20, then we need to find a Z. Then we use the standard normal table. standard normal table. Then after that, we already have the critical value. We know the rejection area and also accepted area. So if you find a test statistics, based on the value, whether it's greater or less than critical value, we may determine whether to reject or accept. So here we need to make a decision to reject or fail to reject a null hypothesis. Again, based on the critical value and the test statistics. Now we say that if the G value is less than or equal to the lower critical value, or if the G is greater than or equal to the upper critical value, then we reject HO, which means it will fall outside the accepted area, brown area. Otherwise, we will fail to reject HO. Then we have to interpret the decision in the context of the original claim. So let's see an example. So here we have a foreman for a construction company records injuries reported by workers during his shift. The following sequence shows that whether any injuries were reported during each month in a recent year. So I represent a month in which at least one injury was reported, and N represents a month in which no injuries were reported. At alpha equal to 0.05, can you conclude that the occurrence of the injury each month is not random? So here, I means there was injury that month, N means there was no injury. So we have I, N, 3N, I, N, N, N. So we can count the number of runs here. We get I 1, and 2, 3, 4, 5, 6. And the total should give us 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because it's for the whole year, 12 months for the year. So again, this question saying that a foreman for a construction company records injury reported by workers during his shift. And he reported once every month for 1 year. So the following sequence show whether an injuries were reported during each month in a recent year. I represent a month in which at least one injury was reported, and N represents a month in which no injuries were reported. So at alpha equal to 0.05, can we conclude that the occurrence of this injury in each month is not random? So we do our hypothesis testing. We start with our HO, the occurrence of the injury is random. HA, the occurrence of injury is not random. Then we have our sequence. So we can see that here we have N1 and N2. So N1 will be the number of eyes. So we have, again, 5. Let's count it. 1, 2, 3, 4, 5. Then we have 7. 1, 2, 3, 4, 5, 6, 7. 7N. Then G will be the number of runs. So we have 1, 2, 3, 4, 5, 6. So number of runs is 6. Alpha is given to us to be 0.05. So again, if I know the size of N1, N2, we can see that they are less than 20. So which means we have to use the critical value table, the critical value for finding the run test table, which is, here we call it table 12. So that's what we said, because N1 is less than or equal to 20, N2 is less than or equal to 20. We use table 12, which is the critical value for finding the randomness. And this is how the table looks. So you can see that in each row, 2, 3, 4, 5, we have 2 different values. So here we have N1 is 5, N2 is 7, and G is 6. So you can see that we go through, the lower critical value is 3, and the upper critical value is 11, because we go to N1 is 5, and N2 is 7. So 5 and 7, that give us 3 and 11. So here we say the lower critical value is 3 and the upper critical value is 11. So we have the above 11, 3, and 11. Now we need to find the test statistics. Remember they said we will reject HO when the test statistics is less than 3 or greater than 11. So first, we know the G is our 6. Here, the reason why we are using the test statistics as G equal to 6, not the formula. Again, the size is less than or equal. N1 and N2 size is less than or equal to 20. So if G is 6, we can see that 6 actually fall inside 3 and 11. So this means we're going to fail to reject HO. We only reject HO if our test statistics value is less than 3 or greater than 11. It's outside the range of 3 to 11. But since 6 is within the range of 3 to 11, we are going to accept HO. So we fail to reject HO. So this means there's a randomness here. At 5% level of significance, you do not have enough evidence to support the claim that the occurrence of injury is not random. It's random. So it appears that the injuries reported by workers during the former shift occur randomly. Again, one thing I want us to get is the step-by-step process of solving. Again, we saw the steps in our earlier. Let's start from here one more time. So performing a run test for randomness, this is hypothesis testing. So the first thing we do is to state our HO and HA, which is the null hypothesis and also alternative hypothesis. Then after that, we specify the level of significance, which is the alpha. Then after that, we can determine the number of data that have each characteristics and the number of runs. So we need to know N1, N2, and G. But there's a condition for N1 and N2. So we said that if N1 is less than or equal to 20 and also N2 is less than or equal to 20, then we use table 12, which will be the table for finding the critical value for number of runs. Otherwise, if it's greater than 20, N1 and N2 are both greater than 20, then we use the standard normal table, But we are going to look for Z. So that's where we calculate the test statistics. This will help us to get a critical value. Critical values set a range for us where we can see accept and also reject HO. So now we know it. So next we look for the test statistics. Now, if the N1 is less than or equal to 20, N2 is less than or equal to 20, then we use the G value. That is the number of runs as our test statistics. But if N1 is greater than 20 or N2 is greater than 20, then we need to find a Z. So Z is G minus mu G over standard deviation G or sigma G. Now we need to find the mu G and sigma G. Since we know the value of N1 and N2, we can find it. So after that, we're going to make our decision to reject or fail to reject null hypothesis. And we said that if G is less than the lower critical value, which means is outside the boundary, or if G is greater than upper critical value, then we need to reject HO. Now, if it fall within, then we have to fail to reject HO. We need to accept HO. Then we interpret our results. So the example here is a foreman for a construction company records injuries reported by workers during his shift. The following sequence shows that whether any injuries were reported during each month in a recent year. I represent a month in which at least one injury was reported, and N represents a month in which no injury were reported. At alpha equal to 0.05, can you conclude that the occurrence of injury each month is not random? So this is what is given to us, 12, which means 1 year each month. So I can tell I1 run, N, 2 run, I 3, 4, 5. So we have 6 runs. And N1 will be 1, 2, 3, 4, 5. and N2 will be 1, 2, 3, 4, 5, 6, 7. So first we state our HO and HA. The occurrence of injury is random. The occurrence of injury is not random. Then we write the sequence down. When we write the sequence down, we can find N1. N1 will be the number of eyes. So we have 1, 2, 3, 4, 5. Then N2 will be number of ends. So 3, 4, and another 3, so 7. Then G will be the number of runs, which is eyes 1, ends 2, Y 3, 4, 5, 6. So that will be 6. Alpha is 0.05. So since n is less than or equal to 20, both n1 and n2, we need to use the table 12, which is the table for finding the critical value for runs test. If it's greater than 20, n1 and n2 is greater than 20, then we use the z-test, standard normal. So here we go to the table. N1 will be the row, so N1 is 5, we go to the 5th row. N2 is 7, so we have our critical value 3 to 11. The lower is 3, the upper limit is 11. So we can see again, N is 5, and N1 is 5, N2 is 7. So any value that falls outside 3 to 11 will mean we are going to again reject HO. If it falls within 3 to 11, inside, let's say 4, 5, 6, 10, then we are going to accept HO. So we look for the test statistics. In this case, the test statistics will be 6. Why? Because the number of runs is 6. And why we are using G? Because again, the n size is less than or equal to 20. When the S size again is greater than, both N1 and N2 is greater than 20, then we use the Z. We find a Z. So since 6 is within 3 to 11, then we are going to accept HO. We fail to reject HO. So here we say at 5% level of significance, you do not have enough evidence to support a claim that the occurrence of injury is not random. So it appears that the injuries reported by workers during the foreman shift occur randomly. So this is another example, again, using the run test. Here you want to determine whether the selection of recently hired employees in a large company is random with respect to gender. The genders of 36 recently hired employees are shown below. At alpha equal to 0.05, can you conclude that the selection is not random? So again, the same step we are going to do. We state our HO, HA. HO is always random, HA is not random. So the selection of employee is random. HA, the selection of an employee is not random. Then we look for the number of runs. So we have MM for F, or the M, F, M, F. So I can count the runs to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the number of runs will be 10. N1 will be the number of Fs, female. So we count female 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 female. Then we count the number of M's, which will be N2, 1, 2, and we have 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 20. So we have 22. So now we check the G. As we said earlier, G will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So G is 11. Now here we have our N1, we have our N2, we have G11. Now we need to find the alpha, which is given to us to be 0.05. Now we need our critical value. But remember the critical value here, we are using the Z. Why are we using the Z table? Because N2 is greater than 20. Remember we use the critical value for run test table. if N1 and N2 both are less than or equal to 20. But since N2 is greater than 20, we use the Z. So critical value, straightforward with Z, all we do is say 1 over alpha over 2. Then we look at our table. And this is random or not random, so it's two-way. So we divide 0.05 into 2, 0.025, 0.025. And we get a Z to be 1.96, positive and negative. So now we need a test statistics, and we know there's a special formula for that. So we need to find the mu G, which is 2N1 times N2 over N1 plus N2 plus 1. So we have the value to be 18.11. Then we plug in for the standard deviation G. And when we plug all the value, we get 2.81. So now we can find 11 minus 18.11 over 2.81. And that will give us negative 2.53. So again, as we said earlier, since N1 is less than 20, but N2 is greater than 20, which was 22, we need to use the standard normal table. So we need to find a Z. We already know the G, that is the number of runs. So mu G, the formula is given, we plug in the values. We already know N1, N2, so we plug in the values. Sigma G also, all we need is the N1 and N2, we plug in the values. So after we get the mu G and the sigma G, we can find a Z, which will be G over mu G over sigma G. So we get negative 2.53. So now we go back and go and look for where negative. So negative 2.53 fell in the blue area. So here we are going to reject HO. We said if it fell within the values, within, here our value will be from negative 1.96 to positive 1.96. So any value, if the value is greater, if the test statistics is greater than 1.96 or lesser than negative 1.96, then we reject HO. Remember always the brown region is the accepted HO region. So we interpret our answer saying that you have enough evidence that 5% level of significance to support the claim that the selection of employees with respect to gender is not random. So again, this will be the conclusion for our lectures. And these lectures, again, we learn how to use the run test to determine whether a data set is random. Again, this is our final lecture for our statistics class. And again, wish everybody the best. We're soon going to have the final exams, which will be next week. Again, in this course, we learn everything from descriptive statistics, probabilities, inferential statistics. In inferential statistics, we learn both the parameter testings and also we learn the non-parameter testing. And we went through the concept of hypothesis testing, confidence interval, etc. So again, wish everybody good luck and thank you for the course, your time.